One thing that I wanted to bring up as we talk about injector is thinking about temperatures. The goal of the injector, right, is to make sure that things get into the gas phase. So whatever we're injecting, now these syringes that we use, they're called gas tight syringes. And so if you had a gas sample, you could inject a gas directly onto the column, and that's a-okay. But a lot of times we're more interested in solution phase stuff. And so we're injecting solutions onto the column, and we need to make sure that those solutions vaporize before we put them on the column. And so the inlet temperature is often quite high, at least high enough to vaporize the solvent. Right? Now we have all boiled water, right? Made a little pasta. And you know that if you hold water at 100 degrees, it just boils along. But if you have a hot pan and that pan heats up above 100 degrees and then you put water in it, that water goes to steam real quick, right? Because that pan's not at exactly 100 degrees, the boiling point, it's pretty much well above that. And so this inlet temperature is not, 105 degrees so the water just boils. It's well above that, so that the solvent, water, or whatever it is, pretty much vaporizes instantaneously. And so, vaporize the solvent and then some. And so usually we're talking about 250 degrees C or something like that, right? We're talking about a pretty high temperature relative to the boiling point for water or alcohol or whatever we're dealing with. Okay. Now the column likely will not start that warm, right? Remember, we use temperature gradient to pull stuff off the column. And so the column starts much colder than that. And so what happens is at your low column temperatures, if this part here is 250 degrees and the column is 40 degrees, if your sample, your analyte, is not in the gas phase at 40 degrees, it's just going to stick to that column right there. Right? And really, that's what we want. We want stuff that's not as volatile to stick to the column when the temperature is low, so that it separates from the stuff that is very volatile. Right? And so the inlet temperature is high, right? And we know that the column temp starts low and ramps up. Okay. And whatever temperature it goes to, that sort of depends on the requirements of your particular analytes. But usually something around room temperature, 30 or 40 degrees, is the starting point, and it'll end at a high enough temperature that you're sure all of your compounds have come off the column. Okay. On the other end of the column, the detector, right, we need to make sure that that nothing comes off the column and recondenses on the detector, right? We want it to stay in the gas phase. Once it gets in the gas phase on the column, we want it to stay in the gas phase as we go out. And so the detector temp needs to also stay high. So high enough to prevent recondensation. Okay. And so usually, your injector stays warm, right? The column heats up to some maximum. Let's say the column heats up to 200 degrees C, just as an example. Right? The detector should stay at least 200 degrees C the whole time, and maybe even a touch above 225, 250 degrees. just so that we're sure that nothing comes off the column and then recondenses because the detector is cooler than it was when it was in the column. And so almost all of the detectors that we'll talk about have some sort of heating element. Even in the mass spec, the one that we took apart, you saw that when the GC line came into the mass spec, there was a heater there, so that the mass spec stayed at a high enough temperature so that things didn't condense. All right, so we're going to talk about just a couple of different kinds of detectors. The textbook goes through, I don't know, maybe 7 or 8 different kinds of detectors, and gets sort of into some little nitty-gritty details that are interesting, but not always applicable. The first and probably the most common GC detector is this FID, right? This flame ionization detector. In addition to being the most common, and maybe the reason it's the most common, is because it's also the most applicable, right? We can analyze essentially any analyte. We can detect any analyte that will combust. Right? And so all organic compounds will combust, right? And that's a whole bunch of what we're interested in when we do analysis. There are some inorganic compounds that usually don't get into the gas phase very well anyway. But virtually all organic compounds will combust when we add them with hydrogen, with oxygen. And so, as long as we can get it to burn, we will be set. So in the bottom of our detector here comes the flow from the column, right? We add to it this mixture of hydrogen and air. In some GCs, they use hydrogen as the carrier gas. In some, they use helium and add hydrogen at the end, like in this picture, but it really doesn't matter. The point is that you have that flame burning the whole time, right? And so you have this hydrogen flame that's continuous. One of the interesting things about GCFID is that you can't see a hydrogen flame. It's colorless. And so the only way to really know if your detector is turned on is to put a cold piece of metal over the outlet so that the water vapor that's generated condenses on that metal. And if you see the condensation, then you know your flame is on. But as you pass through this flame, right, unlike in atomic absorption, where we did not want to ionize our atoms, here we absolutely want to ionize our sample. And the sample ionizes in the flame. And that current is detected. And so we generate this current. Here it's showing this negative voltage is attached to a ring. It's almost like that mesh that we saw in the mass spec detector covering, right? So that mesh, and then as the ions pass through it, moving charge generates a small current, and so you make a small current in these little loops of wire, and that's amplified by the electronics. Okay. A few key points about FID. Because it doesn't detect things that don't burn, things like nitrogen and carbon dioxide. Um, it's actually very good for doing sort of air pollution studies, right? Because it doesn't detect air. Um, and so it's good for a lot of studies, but in particular air pollution, because the most common constituents of air are not detectable, right? And it doesn't detect oxygen because oxygen is already being brought in to make the flame go. It's also good for water pollution, right? I'm going to put in water. Because since water is the product of this H2O2 combustion, there's lots of water already in the system. It doesn't really detect water very well. Water is already fully oxidized, and so it doesn't combust in a hydrogen flame. So it's good for pollution studies. It's also very good for hydrocarbons, right? Again, things that burn well. Carbon goes to CO2 very easily, right? The kinds of compounds that don't necessarily work very well in FID are compounds with lots of heteroatoms. I'm going to put that in red. And so the heteroatoms lower the signal. So FID, most common, you have the issue of having hydrogen around the lab. Most labs that do a lot of GC have a hydrogen generator rather than a tank of hydrogen. And so this just takes air around the lab and takes the water in there, electrolyzes it so that you get H2 and O2. And so you make enough hydrogen to run your FID, but you don't have an excess of hydrogen sort of just hanging out in the lab, right? So that's one of the ways that you get around having the danger of hydrogen around. Okay. All right, electron capture. This one is an interesting device because we have some radioactive foil, right? And so this radioactive foil is it's nickel. I think it's nickel 63. It's some isotope of nickel, often, or it could be tritium, right? It could be just coated with a layer of tritium. So I know you've heard about deuterium. We talk about deuterium in organic and things. Tritium is the isotope of hydrogen with 2 neutrons for a mass number of 3. Super radioactive. Doesn't exist very much. And so you end up with a beta emitter. What's a beta particle? Do you talk about radioactivity in physics? Or just not at all? Yeah, okay. Beta particles are electrons. And so we have these electron emitters, essentially. And so they're constantly giving off electrons, even when our analyte is not flowing through. And so there's some background current because those electrons can ionize the carrier gas, depending on what it is, right? Helium's not very ionizable, but if you had nitrogen or neon or argon or something larger than helium, you'd get sort of this background level current. But in any case, the beta particles, which are electrons, ionize the analyte, right? And again, that current is detected. This is good for, let me switch to green. Right. This is good for molecules that have electronegative functional groups. Right. And especially so for halogens. So halogenated compounds, ECD is probably the best detector for those, just because they give such a strong signal in an ECD. And so because of that, you know, it's good for things with lots of halogens in them. It's good for pesticides. Lots of pharmaceuticals have you know, either electronegative functional groups or specifically halogen atoms. And so pharmaceuticals really anything with nitrogen, because nitrogen has that lone pair. He's good at attracting those, catching those emitted beta particles. And so anything nitrogen containing. This is not great for things like just regular old hydrocarbons, right? Like the FID was perfect for hydrocarbons. This is not great for just plain old straight chain hydrocarbons, because they don't have anything that's particularly good at catching that electron. Also, one downside of this is that you have to have a radioactivity license, right? I can never spell license. And so that's, if you're running these kind of samples all the time, sure, it's worth it. But for a place like Wofford, where we might do it once a year as a demonstration, it's not worth it to us. Okay, so we've got one that's good for general organics, the FID. We've got one that's good for electronegative stuff and halogens in particular, the ECD. And so now the one that we actually have at Wofford, a thermal conductivity detector, the TCD. And so the way that the thermal conductivity detector works is that the carrier gas has known thermal conductivity. Right? In other words, if I apply a known amount of energy, a known amount of heat in one location, and measure the heat in another location, if I know that distance and I know what the carrier gas is, I should be able to tell you pretty accurately how much heat I should register on the other in the second position, the detecting position, right? Because we know the thermal conductivity, we know how well heat travels through that material, through that medium, and we know exactly how much heat we're putting in, we should know exactly how much heat we're getting out, right? And so what happens is you have your reference gas is just your carrier gas, right? Without sample, right? So this is your mobile. Yeah, the reason they call it reference is because it's not the mobile phase, right? And so this is, I'll just use helium as our example, right? So our helium is our reference gas. And then the sample gas is the helium plus the sample, right? That's our mobile phase. That's what's coming off the column. So maybe I'll say from column. Okay. These little resisting wiggles here, right, are heater filaments. So heating elements again, it's sort of like that tungsten bulb filament, right? Just resistively heated metal. They're actually physically located in different little cavities of this detector, different chambers in this detector. Right. And so the diagram, the way that they've drawn it here, is a particular type of electronic bridge, and that is not as important to me as knowing that the reference gas is heated over here. Right? So on the left side of our diagram, right, these things are heated up to a certain temperature, right? And then the temperature is measured over here. The way that the detector works is that reference gas should not change ever, right? The amount of energy going through shouldn't ever change. The way that the detector actually detects is that it applies extra power or current, if we want to think about those actual electrons flowing, to the sample filament to maintain the reference temperature. Okay, so as our analog, so we've got our reference gas coming through, just helium, right? The part of time when there's just helium coming off the column, those two are exactly the same. It should take the same amount of energy to heat them to the same temperature, right? As soon as the analyte starts coming off the column, it's going to decrease the thermal conductivity of that sample side of things. As that thermal conductivity decreases, the heating filament has to work harder to maintain the temperature, right? So the analyte coming off causes that temperature to drop, just like, if you've got one of those old-fashioned stoves that still has the metal coils, right? If you heat it up, it gets red hot, right? But as soon as you put a pan on it, it starts to go down in intensity because that heat's being transferred to the pan, right? Same thing happening here. As the analyte flows through, some of that heat is being transferred to the analyte, and so the temperature goes down. And in order to raise that temperature back up, they have to add more power, more current to that sample filament so that it matches the reference. And the amount of current that they add tells us the amount of analyte that's in the sample. Right? And so the amount of current is proportional to the amount of sample. Okay. And again, that's the type we have. I don't know if you remember, but our GCMS has, of course, a mass spec detector in the front column, but it also has a rear column, and that rear column is not hooked up to the mass spec, but it's hooked up to a TCD detector. All right. Now, again, I told you that our textbook goes through a lot of other types of detectors. They focus on a lot of photo detectors, so almost like an atomic emission or an atomic absorption kind of thing. We talked about AA, of course. We did not talk about atomic emission, but it's sort of the reverse of AA. That's chapter 9 if you want to go back and look at it. But it's using light to sort of figure out and detect when there's something other than mobile phase in the stream. To the best of my knowledge, and I don't, I'm not hugely familiar with these kinds of detectors. They don't give molecular information. The emission ones can give sort of atomic elemental information, but they don't give you very good molecular information. Of course, none of this really gives us very good molecular information. And so that's where these last two techniques come into play, right? As we've talked about, chromatography is not really a very good method for determining what's in our mixture. It's mostly a method for separating that mixture into different components so that then we can use other techniques to figure out what's in it. Two of the techniques that are most commonly connected to GC are, of course, mass spec. So GCMS over here, right? And this is GCFTIR, which is a pretty neat little design, right? Again, you've got your sample is heated so that it's at a constant temperature, similar to the way that the HPLC UV-Vis detector flows. You've got your flow through this little channel with the appropriate windows on either side, right? For UV-Vis, they were quartz. Here, they're KBR, so that those infrared beams can pass through. This is called a light pipe, by the way, which I think is funny. And so your sample, your mobile phase is flowing through that light pipe, and the IR is taking a reading every, I don't know, second, every 2 seconds, something like that. Again, this is one of those techniques that couldn't have been done 20 or 30 years ago because FTIRs were not fast enough. And certainly scanning IR was not fast enough to do this. In a scanning IR, it took 20 minutes to take a spectrum. So with the introduction of Fourier transform and that quick computation, now they can take an entire IR spectrum on the order of the amount of time that it takes the mobile phase to flow from one end of this light pipe to the other. So pretty nifty. The GCMS, again, we've talked about this already, but you have your, so this is from the column, right? It passes through this skimmer, we talked a little bit about a skimmer when we did electrospray ionization, and we talked about it in chapter 13. But the way that it works is you've got your, as you go through this nozzle, the lighter atoms have a broader spray as they go through a nozzle. And there's a better word than spray, but I can't think of it off the top of my head right now. Lighter atoms spread more than heavier atoms, right? And since our carrier gas is usually relatively light, helium, sometimes nitrogen, sometimes neon, you know, these are no more than, well, nitrogen's 28 AMU, neon 20, helium 4, right? These are usually lighter than whatever we're looking at. And so we lose most of our mobile phase that way, and the mass spec can sort of focus in on and sort of ignore most of our carrier gas. This junction here that they're showing at the bottom, that is just sort of that thermal connection. So obviously the mass spec is showing it on the left here. And so again, you're coming from the column to the mass spec. They're just showing this junction. So this is our high vacuum seal. Because over here in the mass spec, right, this is that nozzle. I told you it's a first edition book, and it's a little frustrating. Like, to me, the mass spec should be on the same side of the diagram for both of them, right? But anyway, say love you. Okay, so those are coupled techniques in GC. Okay, so for Monday, there's a journal article on a milli whistle. Which is a GC detector that uses essentially like a little flute to detect different analytes. And it's really amusing to me. So it's an interesting article. So take a look at it. And we'll finish up with some non-textbook GC info on Monday. I don't have that ready today, so you get an extra 13 minutes of free time. Questions on this last bit of stuff out of chapter 16? Hearing none, have a joyous weekend.
Yeah.
Bye, thank you.
Yep.
Dr. Dave.